This video is about double angle identities, and we're going to start by developing them, or at least seeing where they come from based on other identities we already know. For example, let's start with the double angle identity for sine, which would start with sine of 2a. So there's the double angle part of this, the doubling the angle inside 2a. So the sine of 2a we can develop into a formula if we use a previous formula. Namely, isn't the sine of 2a the same thing as the sine of a plus a? A plus a is 2a, so those are equivalent. And in that case, this is now just the sum of angles identity for sine, which we already know. So let's write that out, but we're used to seeing that identity with an a plus b in the input, and now it's an a plus a, which will look a little redundant, but we're going to still use that same formula, which would turn into sine of a cosine of a plus cosine of a sine of a. Now, algebraically, if I take each of these terms and just look at them closely, notice this is sine of a times cosine of a plus cosine of a times sine of a. Well, given the commutative property of real numbers, cosine of a times sine of a would be the same thing as sine of a times cosine of a. So really, I could switch the order of these two factors in either term. I'll just pick the second one. And if I did, I could rewrite this as sine of a times cosine of a plus sine of a times cosine of a again. Again, just switching those two factors at the end there in that second term. Well, if I write it that way, hopefully it's clear that these terms are exactly the same. Sine a cosine a plus sine a cosine a, which would mean if I combine those as like terms, I could write this as 2 sine of a cosine of a. So this is our double angle identity for sine. We start with sine of 2a, and it turns out to be equivalent to 2 sine a cosine a. Let's now develop a formula or formulas for the cosine double angle identity. So if we start with cosine of 2a, there's our double angle identity. We're going to expand this or turn it into something just like we did with sine. I'm going to call this cosine of a plus a, which means now we can use the sum of angles identity for cosine. And if I do, I would rewrite this as cosine a cosine a. Again, normally it's a plus b, so we'd have cosine a, cosine b, but we're both using them as a this time, so cosine a, cosine a, and then the sine is the opposite, so we had a plus to begin with, now we'll turn it into a minus in this identity, and then it would end up with sine of a, sine of a. If I do a little simplification here, cosine a times cosine a is really just cosine squared of a, and similarly sine of a times sine of a would be sine squared of a. And so this gives us our first double angle identity for cosine. Cosine squared a minus sine squared a. And you can see right there where it comes from. Now, from this very identity, we could get a couple more since we know other identities already. Namely, if you recall, let me just write it up over here, the Pythagorean identity. Remember our sine squared of x plus cosine squared of x equals 1. That was our foundational Pythagorean identity. If I use that identity and solve it for, let's say, cosine squared, wouldn't I just take this sine squared and bring it to the other side? And if I did, I would have cosine squared of x equals 1 minus sine squared. We've seen and used that already. So I'm going to do that and replace this cosine squared in our current identity with that very expression, which would give me the following. Let me just split this off here. So I could say this is also equivalent to cosine squared of a being 1 minus sine squared of a. That would be replacing this cosine squared of a. But then if I continue by subtracting this second sine squared of a as we have up here, and then combine like terms, I get another form of this identity, which would be 1 minus 2 sine squared of a. So this turns out to be another form of our cosine double angle identity that's sometimes very useful. Now if I do the same thing, but this time work on the sine squared term up here, I'll split off and get yet another identity. For instance, let me rewrite what we have here in our original identity with cosine squared of a minus, but now instead of sine squared of a, I'm going to replace it with the Pythagorean equivalent. If I solve this Pythagorean identity for sine squared by moving the cosine squared to the other side, I could turn sine squared into 1 minus cosine squared of a. Now notice this time I had to use parentheses with that little substitution because this negative sign really should be distributed to both of those terms, which would result in cosine squared of a minus 1 plus cosine squared of a. Now if I combine the cosine terms that are like, in that I'll get a next step, which would be 2 cosine squared of a minus 1. And so this turns out to be yet another equivalent form of our double angle formula for cosine, and all three of these, which are now all boxed up, turn out to be equally convenient depending on the situation. So sometimes we may want to use the first one, second one, third one, but they're all three various options for cosine double angles. Let's now take a moment and develop the double angle formula for tangent, and you'll see some similarities in this by now since we've already done sine and cosine. For tangent of 2a, we'll again split that up and turn it into the tangent of a plus a, like we've been doing for sine and cosine. And now, of course, we'll use the sum of angles identity for tangent that we know. Remember, we're used to seeing this with an a plus b in it, but it's the same formula now, just with an a plus an a. So this will turn into tangent of a plus tangent of a all over 1 minus tan a tan a. Again, we're used to seeing an a and a b in this, tan a plus tan b over 1 minus tan a tan b. But they're both a this time, given the way we split up this original input. So we're going to use this and then just combine some like terms here. In the numerator, if you add tan a plus tan a, you get 2 tan a. And then down below in the denominator, this will be 1 minus, and then tan a times tan a would be tan squared of a. And so this result here will end up being what we use for our double angle identity for tangent. Let's now take a look at an example that might use one of these double angle identities. Here it is. It says if cosine of x is equal to negative 7 over 25, and then tangent of x is positive or greater than 0, find sine of 2x. Alright, so we're going to focus on the goal, the results that we're looking for, which is sine of 2x. And observe that that's a double angle, and we know a formula for that by now. So I'm going to write this out to start and say that sine of 2x, which is what we're trying to find here, we know that's equivalent to 2 sine of x cosine of x. So that's just using our identity directly. Sine of 2x is equal to 2 sine x cosine x. Now, some of this we'll be able to substitute and replace. Remember, our goal is to find sine of 2x, which is really all of this stuff here. The 2 will stay in front. Sine x we don't know yet, so I'm just going to leave that as sine x. But cosine x was given in the beginning as negative 7 over 25. Now, all we have to do is find sine of x, and using the fact that tangent of x is positive will help. If we just draw a little axis with some quadrants on it, we'll recall that, first of all, cosine is negative in our given value here. That means automatically we're in quadrants 2 or 3. But then tangent is positive, which will restrict us down here to quadrant 3. So we know we're in quadrant 3 with the given information, and we can now just construct a triangle, a right triangle, with a vertex here at the origin. And if cosine is given as negative 7 over 25. Remember, we could put our little angle x in the interior corner of this triangle here. And if we did, cosine is adjacent over hypotenuse, so we'd have negative 7 over hypotenuse would be 25 down here. And if that's the case, we could find this other missing side using the Pythagorean identity, which would state that negative 7 squared plus, I guess I'll give it a name, how about y, plus y squared would equal the hypotenuse squared, which is 25 squared. So if we simplify this, we'll have 49 plus y squared equals 225. If we subtract 49 from both sides, we'll get y squared equals 176. And then if we take the square root of both sides, we'll have y equals plus or minus, technically, the square root of 176. We'll call this plus or minus, and then 176 happens to have a perfect square factor, which is 16. 176 happens to be 16 times 11. And so we can reduce this to say y, the value of this leg of our right triangle, would be plus or minus, and then square root of 16 is 4, and then the square root of 11 can't be reduced, so we'll leave it just like that. Now, let's also consider what quadrant we're in. If we're in quadrant 3, then this y value here, this vertical side of the leg, should be negative. So I'm going to use only the negative of this plus or minus option. And if that's the case, let me go back to our triangle and label it. We know this is negative 4 root 11. Okay, so we'll use that now to construct a ratio for sine of x. Of course, sine is opposite over hypotenuse. So if we plug the appropriate numbers in here, we'll have the 2 in front, and then sine of x being opposite over hypotenuse will be negative 4 root 11. That's what we just found as that side length there. And then the hypotenuse, of course, is 25. Now we'll bring down the value we already knew for cosine, which is negative 7 over 25. And then just simplify this with the arithmetic. Negative times a negative would be a positive. And then if we multiply the constants together all in the numerators, we'll have 2 times 4, which is 8, times 7, which is 56. So 56 times our root 11 up there, all over 25 times 25 is 625. And that is how we'll have to leave it. 56 over 625 is not reducible. If it was, of course, we would reduce it. But here we go. So we found ultimately the sine of 2x by using the identity and then finding each piece of that identity appropriately as we know how. Let's look at another example where we're given this. If the sine of 2 alpha is negative 8 over 17 and 2 alpha is stuck between 180 degrees and 270 degrees, find cosine of alpha. Alright, so let's take our given information and notice that the first thing we're given is actually a double angle identity, the sine of 2 alpha. Okay, we know what that means. In fact, let's write out the identity right here. We know that the sine of 2 alpha, using our identity, is the same as 2 sine alpha cosine alpha. What we also know is that sine of 2 alpha is equal to negative 8/17. So I'm just going to substitute sine of 2 alpha with that very number. So negative 8 over 17 is equal to 2 sine alpha cosine alpha. That's just doing a substitution there. And now notice, we want to find cosine alpha. Okay, it's right there. But notice that's also disappointing because we don't know sine alpha. If we did, if we knew sine alpha, I could just plug in a number for it and then solve for cosine alpha and we'd be done. But we don't know sine alpha, at least yet. Now let's also consider what we've been given, which is that 2 alpha, okay, notice 2 alpha is stuck between 180 and 270. Okay, that's quadrant 3. We'll have to use that at some point. There's really nothing else we're given. So notice that if I have sine of 2 alpha in the beginning, I've already used its identity. I need to somehow find a way to get sine alpha, not 2 alpha, out of this. So no, you can't just divide by 2 here and here. It doesn't work like that, okay? You can't just divide by 2 to get rid of this 2 in the sine of 2 alpha. Rather, what we're going to do is actually pull back the Pythagorean identity And notice that we could also say that the sine squared of 2 alpha plus the cosine squared of 2 alpha is equal to 1. Again, that's just the Pythagorean identity. Let's proceed with this identity. Remember that sine squared of 2 alpha is the same thing as sine of 2 alpha all squared. That's just a different way to write the same thing. So then I'll copy down the rest, plus cosine squared of 2 alpha equals 1. But then sine of 2 alpha is a value we were given at the beginning. So we can use it and just substitute sine of 2 alpha as negative 8/17. So let me do that and turn this expression into negative 8 over 17. Of course, that's all now still squared, plus cosine squared of 2 alpha equals 1. Now let's go ahead and square this fraction, which would give us 64 over 289. Copying the rest, we'll have plus cosine squared of 2 alpha equals 1. Alright, so notice we can solve for cosine of 2 alpha here. Now, it may or may not be clear yet where we're going with that, but let's at least do that. If I subtract the 64 over 289 from both sides, I'll end up with cosine squared of 2 alpha equals 225 over 289. There's just a little fraction work to get that. It's 1 minus 64 over 289, okay, to get that. Then we'll take the square root of both sides and end up with cosine of 2 alpha would be then plus or minus. We'll have to deal or decide which one we'll use in a minute. Plus or minus, the square root of 225 is 15, and the square root of 289 is 17. Now, let's decide on our sign, our SIGN here, the plus or minus, before we proceed here, just to clean this up. Now notice, if you go back to the original, one of the givens was that 2 alpha was stuck between 180 and 270. Now remember, if you take a look at the quadrants, that's quadrant 3 over here. So in that quadrant, cosine would be negative. So that'll tell us exactly which one we have to use. So then, if the cosine of 2 alpha is equal to negative 15/17, that's great. But remember, I'm trying to get to sine alpha out of this. Not sine 2 alpha, just sine alpha. So is there a cosine double angle identity I could use to replace cosine of 2 alpha in a way that would at least introduce a sine alpha that we could probably solve for? Now, you'll recall cosine of 2 alpha is an identity. The double angle for cosine has 3 different options. If you look at them carefully on the formula sheet for cosine double angle identities, of course we developed them earlier, but if you just look at the sheet, you'll notice one of them does have a sine alpha in it. So if I replace cosine of 2 alpha with 1 minus 2 sine squared of alpha, that's just a double angle identity replacement for cosine right there. Okay, so that'll equal, now we know it's going to be negative 15 over 17. Now I've introduced a sine of alpha. Notice it's squared, sure, we can get rid of that eventually, but it's not even a 2 alpha anymore, it's just sine alpha. And that was using identity to replace the cosine 2 alpha. So algebraically, if I want to solve for sine of alpha here, I'll subtract 1 from both sides and then divide by negative 2. That would give me sine squared of alpha equals a 16 over 17. You can double check the numbers on that. That's just some arithmetic of solving for sine squared alpha in this equation. Then, of course, I would want to take the square root of each side. Now, that's going to give me sine of alpha equals a plus or minus 4 over root 17. Now we have to decide whether we're going to use the plus or minus. Now, notice if you go back to the beginning, we were given some information about alpha, but actually it was in terms of 2 alpha. This inequality told us, and we already used that we were in quadrant 3, or at least that 2 alpha is in quadrant 3. So what about alpha? Because that's what we have now here at the bottom with sine alpha equals plus or minus 4 over root 17. Which quadrant is alpha in? And that will help us determine whether to use the plus or the minus. So we're going to use just some basic inequality work. If I take this original inequality that we were given, which was that 180 is the boundary on the left. We have 2 alpha between 180 and 270. That's what we were given, and it's in terms of 2 alpha. But if I want to know where alpha is, we can just do some basic inequality work here by dividing everything by 2. Okay, if we do that, we'll get then, of course, 90 less than or equal to alpha, which is less than or equal to 135 degrees. So that tells us something about alpha. And it was not given directly, but it was implied by the original given inequality here. If we just solve for alpha by dividing by 2, as we just did, we know exactly where alpha should be. So if we just draw a little coordinate axis here, we'll know alpha is between 90 and 135. Now 90, of course, we know is right up here vertically. 135 would be halfway through quadrant 2. So alpha's got to be somewhere here. Now, if that's the case, all we're trying to determine is if the sign of alpha is positive or negative here, to know which option to use that we have. But as you can tell, where that is, which is only part of quadrant 2, that would be where sign of alpha is positive. So we know exactly which of these to use. Okay, so finally, we know what sign of alpha is. We can go back up where we started here and replace it. So now we know that negative 8 over 17 is equal to 2 times sine of alpha, okay, which we've now figured out is positive 4 over root 17, times cosine of alpha, which is what we're trying to find, so we're going to leave that as cosine alpha. But now we're happy because we can solve that. We were sad, now we're happy. We can solve that for cosine alpha. Arithmetic is not too bad here. This turns into negative 8 over 17 equals, if I multiply these together, 2 times 4 is 8 over root 17 times the cosine of alpha. And then if I just multiply by the reciprocal of this fraction, I should end up with cosine of alpha equal to negative 8 root 17 over 8 times 17, but then these 8's would cancel. So ultimately I should get cosine of alpha is equal to negative root 17 over 17, which can't be reduced, so we're good. That's exactly what we were hoping to find.